Welcome everyone and thank you for attending this session. My name is Nikolaou and I'm a student at the National Competition University of Athens. Today I'll be presenting our integrated aerostructural and thermal design framework for a TPMS-Core composite nose cone intended for experimental rocketry. What makes this work interesting is that it combines modern additive manufacturing, specifically triple periodic minimal surface lattices, with classical composite engineering and a complete ANSYS-based simulation chain. The goal is not simply to design a geometric nose cone, but to engineer a lightweight, stiff, and thermally reliable structure that can withstand aerodynamic pressure and vibrational loads typical of a small amateur or student research rocket. The framework we propose allows us to trace the influence of aerodynamics, homogenized lattice mechanics, composite layups, and thermal effects within one consistent analysis pathway. This helps reduce uncertainty and prepares the design for future manufacturing and testing. The motivation stems from the limitations of common fabrication methods used in student and experimental rocketry. Purely 3D printed nose cones made from PLA, ABS or PETG are convenient and easy to produce, but they tend to deform under aerodynamic loading, soften at moderate temperatures, and lack predictable structural behavior. On the other hand, fully composite nose cones, while exceptionally strong, require careful layup design, added tooling, and more engineering effort. Our approach aims to combine the best of both worlds by using a very thin composite facet to provide high stiffness and strength, supported by a TPMS core that stabilizes the skins and prevents buckling. This sandwich approach significantly increases stiffness to mass ratio while keeping manufacturing accessible. To evaluate this design, we use a fully integrated ANSYS workflow linking CFD-derived pressure loads, material design homogenization for TPMS, composite ply analysis, and thermal simulation. This reduces the guesswork and allows us to refine the structure before any physical prototyping. The structural architecture is a classic sandwich construction adapted for small-scale aerospace components. We use two 0.15mm carbon fiber facets which provide most of the bending and in-plane stiffness. Between them we incorporate a 1.5mm gyroid TPMS core. Gyroid lattices are extremely efficient because they feature continuous curvature and uniform load paths, unlike random infill or honeycomb structures. One of the major advantages of TPMS core is that their stiffness and density can be tuned simply by adjusting the relative density parameter. This allows us to tailor the mechanical response to match specific mission requirements without changing the outlet geometry. The combination of these facets and the lattice results in a structure that is exceptionally stiff for its weight and inherently resistant to local buckling. This makes it an excellent candidate for components like nose cones, which must withstand aerodynamic pressure and vibration while remaining very light. To properly simulate a TPMS structure, we cannot directly run a full 3D analysis of all the lattice truss as it would be far too computationally expensive. Instead, we use ANSYS Material Designer to build a representative unit cell of the gyroid lattice and apply periodic boundary conditions. This allows us to derive an equivalent orthotropic material with stiffness shear moduli and Poisson ratio that actually represents the mechanical response of the full lattice. For a chosen relative density of approximately 8%, the homogenization produces an effective Young modulus around 59 MPa, shear modulus near 25 MPa, and density of 82 kg per cubic meter. These values match well with published experimental data for polymer TPMS structures. Once homogenized, the material model replaces the complex lattice geometry and can be used directly in static, dynamic, and thermal analysis. This greatly simplifies the fair while preserving the key physics of the TPMS behavior. The composite facets are modeled using ANSYS ACP pre-post with a quasi-isotropic layup of 0 and 90 degrees. This configuration provides balanced stiffness which is ideal for components that experience multidirectional loading. The carbon fiber material properties, longitudinal modulus, transverse modulus, shear moduli, and strengths were added along with the necessary thermal properties such as thermal conductivity and specific heat. These thermal values are required to support the transient thermal analysis and ensure the composite behaves realistically when exposed to aerodynamic heating. Fair evaluation uses established criteria including Chai, Hill, Chai-Wu, and Hassin. These methods allow us to evaluate different failure modes, such as fiber tension, fiber compression, matrix cracking, and shear failure at the laminar level. By combining the laminate definition with a homogenized core, we obtain a fully consistent model of the sandwich cross-section that supports both structural and thermal loading. The CFD portion of the project is not meant to optimize the aerodynamic shape of the nose cone. Instead, its primary purpose is to provide accurate pressure distribution along the external surface that can be transferred into the structural fair. We use ANSYS Fluent to simulate axisymmetric external flow at Mach numbers from 0.3 to 1.2, covering subsonic to mild transonic regime. A structured mesh with an inflation layer ensures Y plus values close to 1, allowing the SSTK omega turbulence model to accurately resolve the boundary layer. The CFD results include surface pressure coefficient maps and integrated drag values, forming the basis for the aerostructural coupling. This ensures that the structural analysis reflects realistic aerodynamic loading rather than simplified or guessed load cases. The structural analysis is performed in ASYS workbench, using a combination of a layered shell element for the composite skin and solid elements for the homogenized TPMS-Core. A cohesive interface is inserted between the skin and the core to capture interfacial shear transfer and potential delamination, an important failure mode in sandwich structures. The base of the nose cone is fully constrained to replicate the attachment point on the rocket body. We then apply the CFD mapped aerodynamic pressure, which provides realistic distributed loading. This modeling approach captures bending, membrane stress, shear transfer through the core, and potential interface failure. It also allows us to identify buckling modes and natural frequencies, ensuring the structure remains stable under aerodynamic and vibrational conditions. With this setup, we obtain a comprehensive understanding of how the nose cone behaves mechanically. Across the load cases, the nose cones demonstrate extremely high stiffness relative to its mass and size. Under realistic aerodynamic pressures, deflections were extremely small. The composite face sheets showed failure indices far below unity for all Chai-Wu and Hassing modes, indicating very large safety margin. The TPMS core itself remained within elastic limits and no core shear collapse was predicted. These results confirm that the sandwich architecture performs exceptionally well. The likely limiting mechanisms are not global bending, but rather local phenomena such as core crash, adhesive failure, or interface debonding during extreme loading or manufacturing imperfections. This gives us a clear direction for future physical testing and refinement. Transient thermal simulations are planned but were not completed within the available project timeframe. They will be included in the next phase of this work. In summary, we developed and demonstrated an ANSYS-based workflow that integrates CFD, TPMS homogenization, structural analysis, and in the near future, thermal evaluation. The TPMS core provided excellent stiffness to mass performance, while the carbon fiber skin carried the major loading with very high safety margin. The sandwich structure showed minimal deformation under aerodynamic condition. This integrated approach reduces uncertainties, supports efficient design iteration, and prepares the structure for experimental validation. It also demonstrates the potential TPMS-based sandwich composite in line with aerospace application beyond just the nose cone. Looking ahead, future work will focus on selected extension of the current framework. This includes non-linear effects in the TPMS core, experimental testing to support the numerical models, and transient thermal analysis for short duration flights. Overall, the aim is to gradually move from purely numerical validation towards a targeted experimental verification. Thank you for your time and attention. I'm happy to answer any questions.